What if I told you that right now, at this very moment, the universe is actively preventing you from moving too fast? Not because of friction, not because of air resistance, but because reality itself has a built-in speed limit, and if you could somehow break it, the entire fabric of existence would tear apart around you? Here's something that will absolutely blow your mind. In 1905, a patent clerk named Albert Einstein discovered that the universe doesn't just discourage infinite speed, it literally makes it impossible. And the reason why is so bizarre, so counterintuitive, that when he first published his theory, even some of the greatest scientists of his time thought he'd lost his mind. But here's what's truly terrifying. Einstein proved that if you could somehow reach infinite speed, you wouldn't just break the laws of physics. You would become infinitely massive. Time around you would stop completely. And from your perspective, the entire universe would compress into a single infinitesimal point. You would essentially become everywhere and nowhere at the same time. Think about that. The universe has a cosmic speed limit, 299,792,458 meters per second, the speed of light, and it's not just a suggestion. It's an absolute barrier that gets harder and harder to approach the closer you get to it. Like trying to run through water that gets thicker with every step until it becomes solid concrete. And in the next 3.5 hours, I'm going to show you exactly why this happens, what it means for the nature of reality itself, and how this single fact about speed reveals something absolutely profound about the universe we live in. But before we dive into this mind-bending journey, do me a favor, smash that like button and subscribe to this channel, because what you're about to learn will fundamentally change how you see reality. And drop a comment telling me where you're watching from and what time it is right now. I want to know if you're exploring the mysteries of the universe at 2 a.m. like a true physics enthusiast, or if you're procrastinating at work like I used to do. Let's build a global community of curious minds together. So let's start with a question that seems simple, but opens a rabbit hole deeper than you can imagine. Why can't we go infinitely fast? Your first instinct might be to say, well, we just need a more powerful engine, right? More thrust, more fuel, more energy. And for most of human history, that's exactly what we thought. Ancient humans ran on foot at maybe 15 miles per hour. We domesticated horses and hit 30. We invented cars and reached 100. We built jets and broke the sound barrier at 767 miles per hour. We sent rockets to the moon at 25,000 miles per hour. The pattern seemed clear. Better technology equals higher speeds. Infinitely better technology should equal infinite speed, right? Wrong. And here's where things get weird. In 1887, two scientists named Albert Michelson and Edward Morley conducted what was supposed to be a routine experiment. They wanted to measure how fast Earth was moving through space by detecting differences in the speed of light as Earth moved through what they called the luminiferous ether, an invisible substance that scientists at the time believed filled all of space. Think of it like this. If you're in a car moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing still would measure that ball moving at 80 miles per hour relative to them, right? The speeds add up. So Michelson and Morley figured that if Earth was moving through space and light was traveling through this ether, they should be able to measure different speeds of light depending on whether it was moving with or against Earth's motion. They built an incredibly precise instrument called an interferometer. They measured the speed of light in different directions. And then they got a result that made absolutely no sense. The speed of light was exactly the same, every single time, no matter which direction they measured, no matter how Earth was moving, no matter what they did. Light always traveled at exactly 299,792,458 meters per second. This was like watching someone throw a ball at 20 miles per hour from a car going 60 miles per hour and measuring the ball's speed as 20 miles per hour. Not 80, just 20, as if the car's motion didn't matter at all. Scientists were baffled. They repeated the experiment. Same result. They assumed they'd made a mistake. They hadn't. For 18 years, this result sat there, unexplained, mocking every principle of physics that humanity had developed. Then came Einstein. In 1905, at age 26, while working a full-time job evaluating patent applications, Einstein published a paper that would change everything. It was called On the Electrodynamics of Moving Bodies, and it contained one of the most revolutionary ideas in human history. Einstein said, "What if light's constant speed isn't the weird thing? What if it's actually the fundamental truth of the universe, and everything else, including space and time themselves, has to bend and warp to accommodate it?" Let me say that again, because it's crucial. Einstein proposed that space and time are not fixed, unchanging backdrops against which events happen. They're flexible, malleable things that stretch and compress to ensure that the speed of light remains constant for everyone, no matter how fast they're moving. This was his special theory of relativity, and it immediately explained why Michelson and Morley couldn't detect Earth's motion through space. There was no ether. Light didn't need a medium to travel through, and its speed was an absolute constant that nothing could change. But here's what will blow your mind of what this means. If the speed of light is constant for everyone, and if speeds don't add up normally when you get close to light speed, then something else has to give. And what gives is reality itself. Because what Einstein discovered next was even more shocking. As you approach the speed of light, you don't just experience weird physics. You experience time slowing down, space compressing, and your mass increasing. And these aren't small effects. They're dramatic, universe-breaking changes that make infinite speed not just impossible, but logically contradictory. And we're going to explore exactly how that works in the next section. Stay with me, because we're about to see why the universe isn't just preventing infinite speed, it's protecting itself from a paradox that would tear reality apart. Here's a question that's going to seem simple, but it's going to reveal something profound. What is speed, really? You probably think of it as distance divided by time, right? Miles per hour, meters per second. How far you go in how much time. But here's what Einstein realized. That definition assumes that everyone agrees on what a mile is and what an hour is. And that assumption is wrong. Let me show you why with one of the most famous thought experiments in physics. Imagine you're on a train platform and a train passes by at half the speed of light, about 93,000 miles per second. On that train, someone is bouncing a ball straight up and down. From their perspective, on the train, the ball goes straight up, then straight down. Simple. But from your perspective, standing on the platform, the ball isn't just going up and down. It's also moving horizontally at half the speed of light because the entire train is moving. So the ball is actually tracing out a diagonal path up and forward, and down and forward. Now here's the key. That diagonal path is longer than the straight up and down path. It has to be. That's just geometry. The ball travels a greater distance from your perspective than from the perspective of the person on the train. But remember what Michelson and Morley discovered. The speed of light is constant for everyone. And Einstein extended this principle to say that the laws of physics must be the same for everyone, regardless of how they're moving. So here's the problem. If the ball travels a longer distance from your perspective, but the speed of light, and by extension, all maximum speeds and the laws of physics must be the same for everyone, something has to give. What gives is time itself. For time to work out mathematically, for the physics to be consistent, time must be moving slower on that train from your perspective. The person on the train experiences, say, 1 second passing. But from your perspective on the platform, watching them, maybe 1.15 seconds pass. This isn't a trick. This isn't an illusion. Time is genuinely, physically moving at different rates for different observers, depending on their relative motion. This phenomenon is called time dilation, and it's been proven experimentally hundreds of times. In 1971, physicists Joseph Hafele and Richard Keating took 4 atomic clocks, the most precise timekeeping devices ever created, and flew them around the world on commercial airplanes. When they compared them to identical atomic clocks that stayed on the ground, the flying clocks had lost about 59 nanoseconds, 59 billionths of a second, exactly as Einstein's equations predicted. Think about that. Those clocks experienced less time because they were moving faster. The people on those planes aged slightly less than people on the ground. By a tiny, tiny amount, yes, but measurably, objectively, really. And here's what's absolutely mind-blowing. This effect gets more extreme the faster you go. At 10% the speed of light, time moves about 0.5% slower for you. At 90% the speed of light, time moves about 56% slower. At 99% the speed of light, time moves about 86% slower. And at 99.99999% the speed of light, time is moving 22,000 times slower for you than for someone standing still. But it's not just time that changes. Space changes too. From the perspective of someone watching you zoom past at near light speed, you appear compressed in the direction you're traveling. You look flattened, like a pancake. And from your perspective, the entire universe ahead of you appears compressed. This is called length contraction, and it works hand in hand with time dilation to ensure that the speed of light remains constant for everyone. Think of it like this. If you're moving at 99% the speed of light, and you measure the distance to a star as being 10 light years away, someone at rest relative to that star might measure it as being 70 light years away. You both measure the speed of light as exactly the same, but you disagree on distance and time. Space and time are literally different for different observers. This is why Einstein called it relativity. Space and time are relative to your motion. There's no absolute space, no absolute time. Only spacetime, a unified four-dimensional fabric where space and time are intertwined, flexible, and observer-dependent. And here's where it gets truly bizarre. You know how we said that at higher speeds, time slows down and space compresses? Well, at exactly the speed of light, from the perspective of a photon, a particle of light time doesn't just slow down. It stops completely, and distances don't just compress. They compress to zero. From a photon's perspective, the entire universe is a single point, and the journey from the edge of the observable universe to your eye happens in exactly 0 seconds. A photon exists in an eternal now, experiencing every point along its path simultaneously. And this is why the universe fears infinite speed. Because if you could go faster than light, you would experience negative time. You would arrive before you left. You could violate causality, its self-effect, could precede cause, and the logical structure of the universe would collapse. But wait, if time stops at light speed and space compresses to zero, what happens to your mass? Because that's where things get even more impossible. And that's what we're diving into next. Because Einstein discovered that mass isn't constant either, and that's the final nail in the coffin for infinite speed. Let me ask you something. What does it mean to push something? Seriously, think about it. When you push a shopping cart, you're applying force to accelerate it. The heavier the cart, the more mass it has, the harder you have to push to get the same acceleration. That's Newton's famous equation. Force equals mass times acceleration. F equals ma. Simple, right? Now here's a question that seems equally simple. If you keep pushing that cart with the same force, will it keep accelerating forever? Common sense says yes. If you push continuously with the same force, you should get continuous acceleration. Eventually, given enough time and energy, you should be able to push it to any speed you want, including infinite speed. But Einstein discovered something absolutely shocking. That's not how the universe works. As objects move faster and faster, approaching the speed of light, something bizarre happens. They become harder to push, not because of friction or air resistance, but because their mass increases. Wait, what? How can motion change mass? Mass is mass, right? A kilogram's a kilogram, whether it's sitting still or moving. Wrong again. And this is perhaps the most counterintuitive discovery in all of physics. What we normally think of as mass, what physicists call rest mass, is indeed constant. A kilogram of iron has the same rest mass, whether it's sitting on a table or flying through space. But there's another kind of mass called relativistic mass, and it depends on how fast you're moving. The faster you go, the more relativistic mass you have. And relativistic mass is what resists acceleration. It's what makes you harder to push. The equation that describes this is beautifully simple. M equals m square root 1 v squared per c squared, where m is your relativistic mass, m is your rest mass, v is your velocity, and c is the speed of light. Let me break down what this equation means, because it's genuinely mind-blowing. When you're standing still, v equals 0. The denominator equals 1, so your relativistic mass equals your rest mass. Normal mass, nothing weird. When you're moving at 50% the speed of light, that denominator becomes about 0.866, so your relativistic mass is about 1.15 times your rest mass. You're 15% harder to push. At 90% of light speed, you're about 2.3 times harder to push. At 99% of light speed, you're about 7 times harder to push. At 99.9% of light speed, you're about 22 times harder to push. But here's the kicker. Look at that equation again. What happens when v equals c? When your velocity equals the speed of light. The denominator becomes square root 1 to 1, which equals square root 0, which equals 0. You're dividing by 0. Your mass becomes infinite. This is the universe's ultimate barrier. At the speed of light, you would have infinite mass. And to accelerate something with infinite mass would require infinite energy, which doesn't exist, which means you can't reach the speed of light if you have any rest mass at all. Only things with zero rest mass, like photons, can travel at light speed, and they have no choice but to travel at light speed. They can never slow down, never speed up. They exist only at c. Everything else is permanently locked below the speed of light, asymptotically approaching it, but never reaching it, no matter how much energy you add. And if you're thinking, well, what if we just add more and more energy? Surely we can brute force our way to light speed with enough power? We've tried. At CERN's Large Hadron Collider, scientists accelerate protons to 99.9999991% the speed of light. They pump absolutely enormous amounts of energy into these particles. Each proton has the kinetic energy of a flying mosquito, which sounds small until you realize a proton is 10 times lighter than a mosquito. But here's what's incredible. To go from 99.9999991% to 99.9999999% of light speed, just adding 8 more nines, would require doubling the energy. Doubling it again might add a few more nines, but you could never, ever reach 100%. Even if you used all the energy in the entire universe, you'd just get closer and closer, adding more decimal places, but never reaching C. The universe has created a perfect barrier. In 1964, physicist John Bell proved a theorem that shows why this barrier is so fundamental. He demonstrated that if particles could send signals faster than light, it would allow for violations of causality. You could send information backwards in time. You could create grandfather paradoxes. You could have effects without causes. The cosmic speed limit isn't just a quirk of physics. It's a logical necessity that protects the causal structure of reality. But here's something even more profound that most people miss. It's not really that the universe has a speed limit. It's that the universe has a finite speed for causality itself. Light speed is just what we call it, because light was the first thing we discovered moving at that speed. More accurately, we should call it the speed of causality, or the speed of information, or even the speed of reality. It's the maximum rate at which cause and effect can propagate through space-time. And anything with mass can't reach it, because in a very real sense, things with mass are information, structure, complexity, and all of that takes time to propagate through space-time. Only massless particles, which carry pure energy and no structural information, can move at the speed of causality. Now, you might be thinking, okay, we can't reach light speed, but what about going around it? What about wormholes, or warp drives, or quantum tunneling? Surely there's a loophole? And you know what? You're asking exactly the right question, because in the next section, we're going to explore every single loophole that physicists have ever proposed for beating the speed limit. Some of them are theoretically possible. Some violate everything we know about physics. And one of them might actually work, but the cost is so extreme that it would make faster-than-light travel the most dangerous thing imaginable. Stay with me. We're going deeper. Humans don't like being told no, especially when it comes to exploring the universe. Ever since Einstein revealed that we can't go faster than light, physicists have been searching for loopholes, ways to circumvent the cosmic speed limit. And they've found some absolutely wild possibilities, each one revealing something profound about the nature of reality. Let's start with the one that seems most promising: warp drives. In 1994, a physicist named Miguel Alcubierre published a paper that shocked the scientific community. He showed that Einstein's equations, the same equations that forbid faster-than-light travel, actually allow for a different kind of faster-than-light motion. Here's the brilliant part. You don't move through space. You move space itself. Think of it like this. Imagine you're standing on a long carpet. You can't run faster than light speed across the carpet. But what if you could somehow grab the carpet in front of you and pull it towards you, while pushing the carpet behind you away? From the perspective of someone watching, you'd be moving across the room faster than you could run, but you wouldn't actually be running. You'd be surfing on a wave of moving carpet. Alcubierre showed that you could, in principle, create a bubble of spacetime around a spacecraft. Space in front of the bubble would contract, bringing your destination closer. Space behind the bubble would expand, pushing your starting point further away. And you, inside the bubble, would be standing still in your local spacetime, experiencing no acceleration, no time dilation, no mass increase. You could effectively travel from Earth to Alpha Centauri, 4.37 light-years away, in days or weeks, while only experiencing that same amount of time. You wouldn't be breaking the speed limit because, from your perspective, you're not moving at all. Space is moving around you. Mind-blowing, right? But here's the catch, and it's a massive one. To create this warp bubble, you need something called negative energy, or exotic matter. Not antimatter, which is real and we can create, but matter with negative mass and negative energy density. And we have absolutely no evidence that such a thing exists anywhere in the universe. It would violate every energy condition we've ever observed. It might be fundamentally impossible. In fact, in 2012, physicists Harold White and colleagues at NASA calculated that even if exotic matter exists, you'd need about the mass energy equivalent of Jupiter to create a warp bubble big enough for a small spacecraft. That's about 1.9 times 10 kilograms worth of exotic matter. Even if we could somehow gather that much exotic matter, which we can't deploying, it would be an engineering challenge that makes building the pyramids look like playing with Lego blocks. But here's what's truly wild. The math works. Einstein's equations genuinely allow for warp drives. The universe isn't saying no to faster-than-light travel. It's saying only if you can violate every principle of energy we've ever observed. It's like reality set up a challenge. Sure, you can go faster than light. Just do something impossible first. Okay, what about wormholes? This is another solution, pops right out of Einstein's equations. In 1935, Einstein himself, along with physicist Nathan Rosen, discovered that the equations of general relativity allow for bridges through spacetime shortcuts, connecting distant regions of the universe. Picture spacetime like a piece of paper. 2 points might be far apart on the paper's surface, but if you fold the paper so those points touch, you could poke a hole through both and create a tunnel. That's a wormhole. And here's what's incredible. If you could create and stabilize a wormhole, you could step through it and emerge light years away, effectively traveling faster than light without actually exceeding c in your local region of spacetime. And you knew there was a but. Coming wormholes have the same problem as warp drives. To keep them open, to prevent them from collapsing instantly under their own gravity, you need exotic matter with negative energy density. Physicist Kip Thorne, who won the Nobel Prize in Physics in 2017, spent decades studying wormholes. He calculated that even a microscopic wormhole would require exotic matter, and that any traversable wormhole one big enough for a human to pass through would require amounts of exotic matter that might not even be theoretically possible to gather. Plus, there's another problem: time travel. If you had two ends of a wormhole, and you accelerated one end to near light speed and brought it back, you'd create a time difference between the two ends due to time dilation. Step through in one direction, and you travel to the future. Step through the other way, and you travel to the past. And that creates all the classic paradoxes. Could you go back and kill your grandfather? Could you create causal loops? The universe seems to hate these scenarios, and most physicists believe that some unknown law of physics prevents them. In fact, Stephen Hawking proposed something called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time machines from ever being built, no matter how clever you are. What about quantum tunneling? At the quantum level, particles can do something bizarre. They can pass through barriers they shouldn't be able to cross. An electron can tunnel through a wall it doesn't have enough energy to climb over. This is real, proven, and we use it in technology like scanning tunneling microscopes and flash memory drives. So could we quantum tunnel through space-time and emerge somewhere distant, effectively traveling faster than light? Here's the problem. Even though particles tunnel through barriers, they don't actually exceed the speed of light while doing it. Experiments have shown that the tunneling time is consistent with subliminal motion. The particle isn't teleporting. It's taking a probabilistic shortcut, but causality is preserved. And even if you could somehow scale up quantum tunneling to macroscopic objects, which is probably impossible due to decoherence, you still wouldn't be traveling faster than light. You'd be taking advantage of quantum uncertainty, which operates within the rules of relativistic causality. Every loophole we've explored requires breaking the known laws of physics. Exotic matter, negative energy, violations of quantum mechanics. It's like the universe is taunting us. It's not that faster than light travel is forbidden. It's that it's protected behind barriers that might be impossible to overcome. But here's what's truly profound. These aren't arbitrary restrictions. They're protective mechanisms. And in the next section, I'm going to show you what the universe is actually protecting itself from. Because if we could break the light speed barrier, we wouldn't just be traveling fast. We'd be destroying causality itself. And when causality breaks, reality becomes undefined. Let's talk about something that might sound abstract, but is actually the most fundamental thing in the universe: cause and effect. You drop a glass, it falls. That's cause and effect. You send a text message, someone receives it. Cause and effect. A star explodes. The light reaches Earth 8 years later. Cause and effect. Every single event in the universe happens because something else happened before it. This is called causality, and it's so basic, so fundamental to how we understand reality, that we rarely even think about it. But here's what Einstein discovered. Causality depends on the speed of light. Let me show you why with a thought experiment that will genuinely blow your mind. Imagine you're in a spaceship and you see two events happen. Event A, where a star explodes, and Event B, where a planet detects the explosion. From your perspective, A clearly causes B. The explosion sends light to the planet, which detects it. Cause then effect. Makes sense. Now imagine your friend is in a different spaceship, moving at a significant fraction of the speed of light relative to you. Due to the relativity of simultaneity, the fact that observers in different reference frames disagree on what at the same time means your friend might observe these events in a different order. For slow speeds and normal distances, this doesn't matter much. But for events that are separated enough in space and close enough in time, observers moving at different speeds can actually disagree on which event happened first. But here's the crucial thing. As long as neither event can influence the other faster than light, causality is preserved. Everyone might disagree on timing, but they all agree on causal relationships. If event A can send a signal to event B, everyone agrees that A happened first in a causal sense. The speed of light isn't just a speed limit, it's the boundary of causal influence. It's the maximum speed at which one event can affect another. Now, what happens if we break that barrier? If you could travel faster than light, you could do something absolutely bonkers. You could deliver information from an event before that event happens from another observer's perspective. Let me give you a concrete example that physicist Igor Dmitrievich Novikov worked out in detail. Imagine you're on Earth, and your friend is on a spaceship traveling away from Earth at 80% the speed of light. You send them a message using a faster-than-light transmitter at, say, twice the speed of light. From your perspective on Earth, you send the message at noon, and it arrives at your friend's ship at 12:30 p.m. But here's the thing. Due to relativity of simultaneity, your friend's clock disagrees with yours about what simultaneous means. From their perspective in their moving reference frame, your 12:30 p.m. is actually happening before your noon. So from their perspective, they receive your message before you sent it. Now, your friend decides to reply using their own faster-than-light transmitter, sending a message back to Earth. They send it at what they consider a normal time after receiving your message. But when you receive their reply on Earth, due to the same relativity of simultaneity effects working in reverse, you receive it before you sent your original message. You have received a reply to a message you haven't sent yet. This is called a closed time-like curve, or more simply, a time loop. And it creates an immediate paradox. What if their reply says, "Don't send the message"? Now you don't send it, but then they never receive it. But then they never send the reply. But then you don't know not to send the message. But then you send it. Paradox. This isn't science fiction. This is what Einstein's equations predict would happen if faster-than-light travel were possible. Causality would break. Effects could precede causes. The universe would become logically inconsistent. And this is why the universe fears infinite speed or any faster-than-light travel. It's not about energy or engineering. It's about protecting the logical structure of reality itself. In 1949, mathematician Kurt Gödel, the same Gödel who proved the incompleteness theorems in mathematics, found a solution to Einstein's equations that allowed for closed time-like curves even without faster-than-light travel. It was a rotating universe where you could travel into your own past just by following a very long path through space. When Einstein saw this solution, he was deeply disturbed. The idea that his own equations could allow for time travel paradoxes bothered him for the rest of his life. But here's what's fascinating. Our universe doesn't match Gödel's solution. It's expanding, not rotating in the right way. It's like the universe chose a configuration that prevents these paradoxes. And this pattern shows up everywhere. Whenever physicists find a theoretical way to violate causality, the universe seems to have a mechanism that prevents it. Wormholes? They require exotic matter we've never seen. Warp drives? Same problem. Tolkien's hypothetical particles that always travel faster than light? If they exist, they probably can't interact with normal matter in ways that would transfer information. It's as if there's a cosmic censorship principle. The universe protects causality at all costs. But why? Why is causality so important? Because without it, nothing makes sense. Physics relies on determinism, the idea that if you know the state of a system now, you can predict its future and retrodict its past. If effects can precede causes, determinism breaks down. Prediction becomes impossible. The laws of physics become meaningless. Imagine living in a universe where your actions today could be caused by decisions you haven't made yet, where effects ripple backwards in time randomly, where there's no stable arrow of time. You couldn't think. Thinking requires your neurons to fire in causal sequences. Memory requires causes to precede effects. You remember the past because it caused the present. In a universe without causality, consciousness itself might be impossible. So the universe doesn't just prevent infinite speed out of some arbitrary rule. It prevents it because infinite speed would destroy the foundation of existence itself. But here's a question that's going to twist your brain. If nothing can travel faster than light, how does the universe know to enforce this limit everywhere at once? How do particles billions of light years apart coordinate to ensure causality is preserved? That question leads us to one of the deepest mysteries in physics, and we're going to explore it in the next section, where we discover that space and time might not be fundamental at all. They might be emergent properties of something even stranger. Here's a question that sounds simple, but opens a door to one of the most profound mysteries in physics. What is space? Is it a container that things exist in? Is it a stage where events play out? Is it nothing? Just the absence of stuff? For most of human history, we thought space was just emptiness, a void, a gap between objects. Then Newton came along and said space was absolute, a fixed, unchanging coordinate system in which everything moved. Then Einstein came along and said, nope, space is relative, flexible, and intertwined with time. But here's what modern physicists are discovering. Space might not be fundamental at all. It might be emergent, arising from something deeper, something more fundamental that we're only beginning to understand. And this realization is key to understanding why infinite speed is impossible. Because the speed limit isn't a property of space, it's a property of whatever space emerges from. Let me introduce you to one of the most mind-bending ideas in modern physics, the holographic principle. In the 1990s, physicist Gerard T. Hooft, who won the Nobel Prize in 1999, and Leonard Susskind proposed something absolutely wild. The universe might be a hologram. Not like a literal hologram you'd see at a museum, but rather, all the information in a three-dimensional region of space might be encoded on its two-dimensional boundary. Think of it like this. You know how a holographic image on a credit card is flat, but when you look at it, you see a three-dimensional image. The holographic principle suggests something similar might be happening with the entire universe. The three-dimensional space we experience might be a projection of information encoded on a two-dimensional surface. This sounds like metaphysical nonsense, right? Except it comes from very rigorous calculations about black holes. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered that black holes have entropy, a measure of disorder or information. But weirdly, the entropy of a black hole isn't proportional to its volume, like you'd expect. It's proportional to its surface area. It's as if all the information about what's inside the black hole is somehow encoded on its event horizon, the two-dimensional surface surrounding it. Physicists realized that this might be true universally. The information content of any region of space might be limited by its surface area, not its volume, as if space itself is a holographic projection. And here's where it connects to the speed of light. If space is emergent, if it's not fundamental, but arises from some deeper substrate of information, then the speed of light might be the rate at which information can propagate through this substrate. Physicist Juan Maldacena provided the first concrete example of this in 1997 with something called the ADS-CFT correspondence. He showed that a particular 5-dimensional spacetime with gravity is mathematically equivalent to a 4-dimensional quantum field theory without gravity on its boundary. Think about what this means. Gravity, space, time, and everything we experience in 3 dimensions might be emergent properties of quantum information processing happening in a lower dimensional space. Space isn't a container. It's more like temperature, a large-scale property that emerges from microscopic behavior. And just like temperature breaks down at the molecular level, individual molecules don't have temperature. Only collections of them do. Space-time might break down at the smallest scales. This is where quantum gravity comes in the attempt to unify Einstein's general relativity with quantum mechanics. At scales around 10 meters, the Planck-length spacetime itself probably becomes quantum and granular. It's not smooth and continuous. It's discrete, like pixels on a screen. At these scales, the very concept of moving through space might not make sense. You can't move smoothly through pixels. You jump from pixel to pixel. And if space is pixelated at the Planck scale, then there's a maximum rate at which information can propagate from one pixel to the next. That maximum rate is the speed of light. In other words, the speed of light might be the refresh rate of reality itself. Physicist Seth Lloyd at MIT has calculated that if you think of the universe as a quantum computer, the speed of light is the maximum processing speed, the rate at which the universe can update itself. This gives a completely different perspective on why infinite speed is impossible. You can't process information faster than the universe can compute it. It's not about energy or mass or engineering. It's about the fundamental rate at which reality updates. But here's something even weirder. If space-time is emergent, then the distance between 2 points isn't fundamental either. It's derived from the information-theoretic relationship between those points. Physicist Mark van Raamsdonk showed in 2010 that in certain models, space emerges from quantum entanglement, the spooky connection between particles that Einstein famously hated. When particles are highly entangled, they're close in the emergent space. When they're not entangled, they're far. Space is literally made of quantum correlations. And if that's true, then the reason you can't travel infinitely fast is the same reason you can't be infinitely entangled. There's a maximum rate at which quantum information can spread, which is determined by the quantum speed limit, another name for the speed of light. This is starting to paint a very different picture of reality. Space isn't a stage. Time isn't a river. They're both emergent properties of a vast quantum information network, updating and evolving according to the laws of quantum mechanics. And the speed limit? It's the clock speed of the universe itself. Now you might be thinking, okay, but if space is emergent, where does it emerge from? What's the substrate beneath spacetime? That's the trillion-dollar question in physics. And while we don't have a complete answer yet, we have some candidates. String theory, loop quantum gravity, causal set theory. Each proposes a different fundamental substrate from which spacetime emerges. And exploring these theories reveals something absolutely profound about why not just infinite speed, but even light speed itself represents a boundary between different types of existence. That's what we're diving into next. Because when you understand what light speed really represents, you'll see the universe in a completely different way. I want you to try something right now. Imagine a right triangle. You know, the kind with a 90-degree angle. You probably learned in school that the sides follow the Pythagorean theorem. A squared plus b equals c, where c is the longest side, the hypotenuse. Simple geometry, right? Now here's something that's going to break your brain. Einstein discovered that spacetime doesn't follow the Pythagorean theorem. It follows something different. And that difference is the reason infinite speed is impossible. In normal space, the distance between 2 points is given by the Pythagorean theorem. If you move 3 meters east and 4 meters north, You've traveled square root. 3 plus 4 equals 5 meters from your starting point. But in spacetime, the distance between two events isn't calculated the same way. The equation for spacetime distance, what physicists call the interval, is s equals c yt, x squared, y squared, z squared. Notice anything weird? There's a minus sign. Time is added, but space is subtracted. This isn't just different. It's fundamentally opposite to how space works. And this minus sign changes everything. It means that the geometry of spacetime is not Euclidean. It's what mathematicians call pseudo-Riemannian or Lorentzian. It's a hyperbolic geometry rather than the familiar flat geometry we learn in school. Let me show you what this means practically. In normal space, you can always get from point A to point B if you go far enough. There's no unreachable region. But in spacetime, because of that minus sign, there are events that are fundamentally unreachable from your current position, no matter how much you try. Physicists divide spacetime into 3 regions relative to any event. 1. The time-like region, events that you can reach by traveling slower than light. These are events in your causal future or past. 2. The light-like region, events that you can only reach by traveling exactly at light speed. This forms a cone shape called the light cone 3. The space-like region, events that you could only reach by traveling faster than light. These are events that are causally disconnected from you. That 3rd region, the space-like region, is forbidden. It's not just hard to reach. It's geometrically unreachable within the structure of spacetime itself. Think of it like this. In normal space, all directions are equivalent. North, south, east, west, up, down, they're all just directions you can move. But in spacetime, the time direction is fundamentally different from the space directions because of that minus sign. Moving through time is geometrically opposite to moving through space. And because of this geometry, there's a maximum ratio of space to time that you can traverse. That maximum ratio is the speed of light. Here's an analogy that might help. Think of a mathematical hyperbola. You know, the curve defined by x squared y squared equals 1. This curve has 2 branches, and there's a forbidden region between them. No point on the hyperbola can ever be in that middle region. It's geometrically impossible. The light cone is like that. It's a hyperbolic boundary in spacetime, and the region outside it is geometrically forbidden. You can't reach space-like separated events, not because you lack energy, but because the geometry of spacetime doesn't permit a path connecting you to them that respects causality. Now here's where it gets truly profound. This geometry is what makes the universe consistent. Mathematician Hermann Minkowski, Einstein's former teacher, was the first to fully understand this. In 1908, he gave a famous lecture where he said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He was describing spacetime as a unified 4-dimensional geometric object with this weird minus sign structure. And in this geometry, the path that light takes, the null geodesic, as physicists call it, is special. It's the boundary between the possible and the impossible. Particles with mass always travel on time-like paths that stay inside the light cone, where more time passes than space is traversed. Particles without mass photons always travel on light-like paths that trace out the light cone itself, where space and time are balanced exactly. And no particle can travel on space-like paths outside the light cone, where more space would be traversed than time passes. This isn't a law of physics in the traditional sense. It's a geometric constraint. It's like saying you can't have a triangle with 4 sides. It's not that nature forbids 4-sided triangles. It's that a 4-sided triangle is a logical contradiction. Similarly, faster than light travel isn't forbidden by a law. It's forbidden by geometry. But here's something that will really twist your mind. From the perspective of a photon traveling at light speed, the geometry is even stranger. For a photon, The spacetime interval is 0, s squared equals cyt, x squared equals 0, which means cyt equals x squared. From the photon's perspective, the time it experiences equals the distance it travels in certain units. But since the interval is 0, in a sense, it experiences no time and no distance. The photon exists on the boundary of geometry itself, the edge between the time-like and space-like regions. And here's the truly bizarre part. If you could somehow accelerate past light speed, which you can't, but let's imagine, you would cross from the time-like region to the space-like region. The space-time interval would become negative. You would be in a region where space and time switch roles. Time would become space-like, and space would become time-like. In this region, you would be unable to stop moving through space, just as you're currently unable to stop moving through time. And you would be able to choose your direction in time, just as you currently choose your direction in space. It would be a mirror universe with utterly different physics. But the geometry prevents you from ever getting there. The light cone is an absolute barrier, a geometric boundary that separates two fundamentally different types of existence. Now, you might be wondering, if space-time has this weird geometry, where does it come from? Why does the universe have a minus sign in its fundamental equation? That question touches on one of the deepest mysteries in physics. Why is space-time Lorentzian rather than Euclidean? Why does it have the structure that permits causality and forbids infinite speed? And the answer might be, because any other structure would be unstable or logically inconsistent. We live in a Lorentzian space-time not by accident, but by necessity, because it's the only geometry that allows for stable, causal, consistent reality. And in the next section, we're going to explore what happens at the edge of this geometry, at the event horizons of black holes, where the light cone itself gets warped into impossible shapes, and where the boundary between possible and impossible becomes fuzzy. Let's talk about the most extreme objects in the universe, black holes. You've probably heard that black holes are regions where gravity is so strong that nothing can escape, not even light. And that's true. But here's what most people don't understand. Black holes aren't just extremely dense objects. They're places where the light cone itself, the boundary between possible and impossible motion, gets twisted into a one-way trap. And studying black holes reveals something profound about why the universe enforces the speed limit so absolutely. Let's start with a thought experiment. Imagine you're in a rocket ship, hovering just outside a black hole's event horizon, the point of no return. From your perspective, you can still escape. You fire your engines and accelerate away. The black hole's gravity is pulling you inward, but your engines are strong enough to push you outward. You hover in place. Now you drop a probe toward the black hole. From your safe position, you watch it fall. And here's where things get weird. As the probe approaches the event horizon, you see its clock ticking slower and slower due to gravitational time dilation. Light from the probe gets red-shifted stretched to longer, redder wavelengths. The probe appears to freeze at the event horizon, its clock nearly stopped, its light dimming to nothing. From your perspective, it never quite crosses the horizon. It asymptotically approaches it, getting closer and closer but never reaching it, as an infinite amount of your time passes. But from the probe's perspective, something completely different happens. It crosses the event horizon in finite time, maybe a few seconds. Nothing special happens at the horizon itself. No wall, no barrier, just smooth space. But once it's crossed, something absolutely bonkers occurs. Inside the event horizon, the light cone tips over. The geometry of space-time gets so warped by the black hole's gravity that the future direction of the light cone points inward, toward the singularity at the center. What does this mean? It means that inside the horizon, every possible future path, every time-like and light-like trajectory leads to the singularity. There is no path that leads back out. Not because you don't have enough energy, but because outward is no longer a direction in your future. It's like time and space have switched roles. Outside the horizon, you must move forward in time and can choose to move through space. Inside the horizon, you must move inward through space and can sort of choose your direction in time. The singularity isn't a place in space that you move toward. It's an event in your future that you inevitably reach, no matter what you do. Think about what this means for the speed limit. Outside the horizon, the speed of light defines a cone in spacetime that separates possible from impossible futures. But inside the horizon, that cone has tipped so far over that every possible future is inside the black hole. The cosmic speed limit hasn't changed. Light still travels at sea. But the geometry of spacetime has changed so dramatically that even light itself cannot escape. This is why black holes are so fundamental to understanding the speed limit. They show that the limit isn't just about energy or engineering. It's about the geometric structure of spacetime itself. And when that structure gets warped enough, even light moving at maximum speed can be trapped. Now, here's where it gets even more mind-bending. At the center of a black hole is a singularity point, where the curvature of spacetime becomes infinite, where the laws of physics as we know them break down. What happens there? We genuinely don't know. General relativity predicts that density becomes infinite, spacetime curvature becomes infinite, and tidal forces become infinite. But most physicists believe this is where general relativity breaks down and quantum gravity effects take over. Maybe the singularity isn't really a point. Maybe it's a region of quantum foam spacetime bubbling and frothing at the Planck scale. Maybe it's a tunnel to another universe. Maybe it's a place where space and time dissolve entirely. The late physicist John Wheeler, who coined the term black hole, had a colorful way of describing singularities. The universe suddenly finds itself confronted with an impossible situation. It gets around the difficulty by sweeping it under the rug, hiding it from view behind an event horizon. The speed limit, the light cone, the event horizon, they're all connected. They're all manifestations of the geometric structure of spacetime, and they all serve to protect causality and prevent paradoxes. But here's something that blew physicists' minds in the 1970s. Black holes radiate. Stephen Hawking discovered that due to quantum effects near the event horizon, black holes slowly emit radiation, now called Hawking radiation. Over enormously long timescales, black holes evaporate. And this creates a paradox. Information that falls into a black hole seems to be destroyed when the black hole evaporates. But quantum mechanics says information can't be destroyed. This is the famous black hole information paradox, and it's still not fully resolved. The paradox suggests that our understanding of either quantum mechanics or general relativity, or both, is incomplete. And here's why this matters for our discussion of infinite speed. The information paradox is fundamentally about how information propagates through spacetime. If information is somehow preserved when a black hole evaporates, it suggests a deeper layer of reality beneath spacetime. Perhaps that holographic substrate we talked about earlier. The resolution might be that information doesn't travel through space at all. It's encoded on surfaces, on boundaries, in patterns of entanglement. Space itself is emergent from these information-theoretic relationships. And if that's true, then the speed of light, the cosmic speed limit, is really the speed at which quantum information can propagate through the entanglement network that underlies reality. You can't go faster than light for the same reason you can't process information faster than the hardware allows. The universe has a maximum computational speed, and that speed is c. Black holes are laboratories for studying the limits of physics. They show us what happens when space-time is stretched to its breaking point. And they hint that beneath the familiar world of space and time, there's something deeper, a quantum substrate that processes information at a finite rate. But here's a question that's going to take us even deeper. If the universe has a maximum speed, does it also have a maximum temperature? A maximum energy density? Maximum anything else? The answer is yes, and these maximums are all connected. In the next section, we're going to explore the Planck scale, the realm where all limits converge, where space and time dissolve into quantum foam, and where the very question, how fast, might stop making sense. There's a number that represents the ultimate limit of smallness in our universe. It's called the Planck length, and it's approximately 1.6 times 10 meters. To put that in perspective, an atom is to a human as a human is to the solar system, and the Planck length is to an atom as an atom is to the observable universe. It's incomprehensibly small, and at this scale, everything breaks. Space becomes quantum. Time becomes discontinuous. The very notion of distance starts to lose meaning. And this is where all the speed limits, energy limits, and information limits of the universe converge. The Planck scale isn't just small. It's fundamentally small, the smallest meaningful scale in physics. The Planck length is derived from three fundamental constants of nature. The speed of light, c, Planck's constant, h, which governs quantum mechanics, and the gravitational constant, g, which governs gravity. When you combine these three constants in the right way, you get the Planck length, square root gg per c cubed, approximately equals 1.6 times 10 meters. You also get the Planck time, square root ag per ca, approximately equals 5.4 times 10 seconds. And the Planck energy, square root pc per g, approximately equals 1.2 times 10 GeV. These aren't just small numbers or big numbers. They're the scales at which quantum mechanics, relativity, and gravity all become equally important. They're the scales at which our current theories of physics break down and need to be replaced by a theory of quantum gravity that we don't yet have. At the Planck length, the uncertainty principle of quantum mechanics means that the position of a particle is so uncertain that quantum fluctuations in space-time itself become significant. Space doesn't exist as a smooth continuum. It's a roiling foam of quantum fluctuations, constantly bubbling with virtual particles and microscopic black holes that pop in and out of existence. At the Planck time, the time it takes light to travel one Planck length, the very concept of before and after becomes fuzzy. Time is no longer a smooth flow. It's discrete, granular, quantized. And here's what's crucial for understanding infinite speed. If space is pixelated at the Planck length, then the maximum speed, the speed of light, is literally one Planck length per Planck time. The cosmic speed limit is the universe updating at its maximum frame rate. Think of it like this. If you're playing a video game that updates 60 times per second, the fastest anything can move across the screen is 1 pixel per frame. If something tried to move faster, it would have to skip pixels, which means it would teleport, which violates the continuous nature of motion. Similarly, if the universe updates at the Planck time, nothing can move more than 1 Planck length per Planck time without violating the continuous nature of spacetime. The speed of light is literally the refresh rate of reality. But it's not just space and time that have Planck limits. Energy does too. The Planck energy about 10 GeV is the energy at which creating a particle would create a black hole so small that it would be at the Planck length. At this energy density, the distinction between particle and black hole dissolves. Quantum mechanics and gravity merge. The very concept of a particle, as distinct from spacetime itself, breaks down. We've never created anything close to Planck energy. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches about 10 GeV 15 orders of magnitude below Planck energy. But in the first 10 seconds after the Big Bang, the Planck era, the entire universe was at Planck energy density. Space and time as we know then didn't exist yet. There was only quantum foam, pure undifferentiated quantum information, without distinct particles or forces or even dimensions. This is the true beginning, the edge of knowability. Before the Planck era, the very concepts of before, space, and time are undefined. And here's something that will really blow your mind. Some physicists think the Planck scale isn't just the limit of our current theories. It might be a fundamental limit in nature. If spacetime is emergent from quantum information, then the Planck scale is where the pixels of reality become visible. You can't zoom in further because there is no further. The Planck length isn't the smallest thing in continuous space. It's the grain size of space itself. This means the universe doesn't just have a maximum speed. It has a maximum everything. Maximum energy density, maximum curvature of spacetime, maximum information density. Physicist Jacob Bekenstein proved in 1981 that there's a maximum amount of information that can be stored in any region of space, given by its surface area divided by 4 times the Planck length squared. This is called the Bekenstein bound, and it says that a region of space 1 meter across can contain at most about 10 bits of information. Try to pack in more information, more particles, more complexity, and you'll create a black hole. The information will be hidden behind an event horizon. The universe has a maximum information density, and that maximum is set by the Planck scale in the speed of light. Everything is connected. The speed limit, the Planck length, black holes, information. They're all different facets of the same deep structure. String theory, one of the leading candidates for a theory of quantum gravity, proposes that, at the Planck scale, particles aren't point-like. They're tiny vibrating strings. The different vibrations of these strings correspond to different particles, and the strings themselves are about a Planck length long. In string theory, space-time emerges from the collective behavior of countless strings vibrating in a higher dimensional space. The familiar 3 dimensions of space and 1 of time are just the large dimensions, the ones that grew during the Big Bang. There might be 6 or 7 additional dimensions curled up at the Planck scale, invisible to us. In loop quantum gravity, another approach to quantum gravity spacetime is fundamentally discrete. It's made of tiny loops and networks at the Planck scale. Space is literally woven from these loops, like a fabric made of thread. Both theories agree on one thing. Spacetime is not fundamental. It's emergent. And it emerges from something that operates at the Planck scale with the speed of light as its fundamental speed limit. So we've seen that the universe has limits everywhere. Maximum speed, minimum length, maximum information density, and they're all connected through the Planck scale. But here's a question that's going to take us from physics to philosophy. Why these limits? Why does the universe have this particular structure? Is it the only possible structure? Or could there be other universes with different limits? And more personally, what does it mean for us that we live in a universe with these constraints? How does the cosmic speed limit shape our existence, our possibilities, our future? That's what we're exploring in the next section, where we shift from abstract physics to something deeply personal and profound. I want you to stop for a moment and think about something. You are made of atoms that were forged in stars billions of years ago. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was created in nuclear furnaces deep inside dying stars that exploded long before Earth even existed. Those atoms traveled through space for eons, eventually coming together to form our solar system, our planet, and eventually you. But here's something profound. Those atoms couldn't have traveled faster than light. Their journey took time, real physical time. The cosmic speed limit isn't just an abstract principle. It shaped your existence. It shaped the evolution of the entire universe. And understanding this changes everything about how we see ourselves and our place in the cosmos. Let's start with a simple question. Why does the night sky look the way it does? If light could travel infinitely fast, you would see every star in the universe instantly. The night sky would be uniformly bright, a blinding wall of light from countless stars. But light travels at a finite speed. When you look at the nearest star, Proxima Centauri, you're seeing it as it was 4.2 years ago. The light took 4.2 years to reach you, traveling at 299,792,458 meters per second. No faster, no slower. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. The cosmic speed limit means you can never see the universe as it is now. You can only see the past. The farther you look into space, the further you look back in time. The most distant light we can see, the cosmic microwave background radiation, has been traveling for 13.8 billion years. It's the afterglow of the Big Bang itself, stretched and cooled by the expansion of the universe. We can't see beyond that, not because space ends, but because light from more distant regions hasn't had time to reach us yet. The observable universe, the part we can see, is limited by the speed of light multiplied by the age of the universe. It's a sphere about 93 billion light years in diameter, larger than 13.8 billion light years because space itself has been expanding. But here's the thing, the actual universe is probably much, much larger, possibly infinite. We just can't see most of it because the light hasn't reached us yet. The cosmic speed limit has drawn a horizon around us, a boundary beyond which we cannot see, cannot reach, cannot even in principle communicate with. And this has profound implications. Think about alien civilizations. If they exist, and statistically, they probably do, most of them are beyond our cosmic horizon. We will never know about them. They will never know about us. The speed limit has forever isolated different regions of the universe from each other. Even within our observable universe, the speed limit creates isolation. If there's a civilization 10,000 light years away and they send us a message, we won't receive it for 10,000 years. If we reply, they won't get our response for another 10,000 years. A conversation would take 20,000 years per exchange. For civilizations in different galaxies, it's even worse. The Andromeda Galaxy is 2.5 million light years away. A round-trip message would take 5 million years. The cosmic speed limit means the universe is lonely. We are isolated by vast gulfs of space and time. But here's something beautiful. That isolation is also what makes complexity possible. If information could travel infinitely fast, the universe would be in instantaneous equilibrium. No gradients, no differences, no structure. But because information travels at finite speed, different regions of the universe can evolve independently. Local conditions can differ. Complexity can emerge. Stars can form. Planets can coalesce. Chemistry can happen. Life can evolve. You exist because the speed limit allowed the universe to be diverse, structured, complex. Think about your own life. Every decision you make, every action you take, has consequences that ripple outward at a finite speed. You can't instantly affect the entire universe. Your influence spreads at the speed of light or slower. This creates a causal structure to your life. Your past affects your present, which affects your future. Cause and effect are ordered. Time has meaning. In a universe without a speed limit, with instantaneous causality, the very concept of a self that persists through time might not make sense. You wouldn't have a coherent timeline. Past, present, and future would blur together. The cosmic speed limit is what makes narrative possible. What makes your life story coherent? What allows you to be a continuous being moving through time, making choices, experiencing consequences, learning, growing. The universe fears infinite speed because infinite speed would destroy the structure that makes existence meaningful. But there's more. The speed limit also creates something beautiful, the present moment. Because information takes time to propagate, there's a bubble around you, defined by the speed of light that represents your now. Events within this bubble can causally affect you. Events outside cannot. This bubble expands at the speed of light. Your present moment is constantly growing, encompassing more and more of the universe. But it's also limited. There's always a cosmic horizon you can't see beyond. There's always a future you haven't reached yet. This creates a fundamental uncertainty in life. You can't know everything. You can't see all of space. You can't predict all of the future. And this uncertainty is what makes choice meaningful. If you could see the entire universe instantly, know all causes and effects, predict all futures, would you really have free will? Or would everything be determined, knowable, inevitable? The cosmic speed limit preserves mystery. It preserves the unknown. It creates a space for possibility. Now, you might be thinking, okay, but practically, how does this affect my daily life? I'm not traveling at near light speeds. I'm not communicating with distant galaxies. Why should I care about the cosmic speed limit? And that's exactly the question we're going to explore in the next section. Because the speed of light doesn't just affect astronomy and particle physics. It affects your smartphone, your GPS, your medical treatments, and technologies you use every single day without even realizing it. The cosmic speed limit is closer to your life than you think. Let's explore how. You probably use GPS today, maybe to navigate somewhere, or maybe your phone just used it in the background to tag a photo or check the weather. GPS works by triangulating your position using signals from satellites. Each satellite broadcasts a timestamp, and your phone measures how long the signal took to arrive. Since radio waves travel at the speed of light, multiplying that time by c gives the distance to each satellite. With signals from multiple satellites, your phone can calculate your exact position. Simple, right? But here's what most people don't know. GPS satellites orbit at about 20,000 kilometers above Earth's surface, traveling at about 14,000 kilometers per hour. And at that altitude and speed, relativity matters. There are two competing relativistic effects. First, the satellites are moving fast, so according to special relativity, time on the satellites should run slower than time on Earth by about 7 microseconds per day. Second, the satellites are farther from Earth's gravitational pull, so according to general relativity, time on the satellites should run faster than time on Earth by about 45 microseconds per day. The net effect is that clocks on GPS satellites run about 38 microseconds per day faster than clocks on the ground. Now, 38 microseconds doesn't sound like much. But remember, GPS works by measuring the time it takes for light to travel from satellite to receiver. Light travels 299,792,458 meters per second, which is about 0.3 meters per nanosecond. 38 microseconds is 38,000 nanoseconds. In that time, light travels about 11,400 meters, 11.4 kilometers. If we didn't account for relativity, GPS would accumulate an error of over 11 kilometers per day. After just a few hours, it would be essentially useless. Every time you use GPS, you're using technology that depends on Einstein's relativity. The cosmic speed limit and time dilation aren't abstract concepts. They're built into the system guiding you to the coffee shop, but it goes deeper. Particle accelerators used for cancer radiation therapy accelerate protons or electrons to high speeds, sometimes 80% or 90% the speed of light before slamming them into tumors. Without relativity, radiation therapy would be far less precise and far less effective. Or consider your computer. Modern processors are so fast and so small that electrical signals travel significant distances during a single clock cycle. An Intel Core i9 processor runs at about 5 gigahertz to 5 billion cycles per second. Each cycle lasts 0.2 nanoseconds. In 0.2 nanoseconds, light travels about 6 centimeters. If your processor is 2 centimeters across, signals can't even cross it in a single clock cycle if they're traveling at light speed. And electrical signals in wires travel at about 60 to 90% of light speed, depending on the material. This means that at the highest clock speeds, the physical layout of components on the chip matters enormously. Engineers must carefully design the chip so that signals arrive synchronized, accounting for the finite speed of electromagnetic propagation. In fact, this is one of the fundamental barriers to making computers faster. We've hit a wall where we can't make processors much faster without running into the light speed limit for signal propagation. Or think about the internet. When you click a link, your request travels through fiber optic cables as pulses of light. Light travels through optical fiber at about 200,000 kilometers per second, about 67% of c, due to the refractive index of glass. If you're accessing a server on the other side of the world, say 20,000 kilometers away, the round-trip time, the ping, is at least 200 milliseconds due to the speed of light alone. No amount of technological improvement can reduce that below 200 milliseconds without changing the laws of physics. It's a hard limit set by the cosmic speed limit. This affects everything from online gaming to financial trading to video calls. High-frequency traders locate their servers as close as possible to stock exchanges, sometimes in the same building, because even milliseconds matter when you're competing against the speed of light. And it's not just technology. The speed of light affects biology too. Evolution optimized our neural architecture around signal propagation speed limits. And here's something really profound. Consciousness itself might be limited by signal propagation speed. For information to be integrated, signals must propagate through the system. The speed of that propagation sets a limit on how quickly consciousness can update. Your subjective experience of now, the present moment, might be about 100 milliseconds wide, limited by the time it takes for signals to propagate through your brain and integrate into a unified conscious experience.